Okay. Wow, very full. Lots of folks. How's everyone? Oh, incorrect. How's everyone doing? Okay. Okay. So I gotten some questions about how the extra credit works. So this class is not no grade. At the end of the semester, you will get a grade, right? But the idea is to not focus on the letter of every individual assignment. But we are going to keep track of how well you're doing. So next week, we'll do the check-in. And that is when you're going to make an argument for your grade. I hope you're keeping your homeworks and not destroying them, because you'll need them to make a point about your grade. So if you turn in a homework, you get feedback on it, and you turn it in again, I like to see that. I like to see progress. If I tell you, hey, one sentence answers aren't going to cut it, and you continue to use one sentence question answers, that's fine. That's your choice. But if you get better and you increase how much you're putting into it, then I can see progress. I can see growth, right? That's good. Just did it again. Okay, never mind. So that 2% that you get for going to help sessions for the rest of the semester, that would be like, I think I'm right at the B+ level. May I have an A-? And I'd be like, yes. As opposed to like 2%, right? If you think about what that really means, it's like an extra homework, right? Questions? Yeah.
So said we can return in assignments with improvements. Is there a certain time frame for that? Like the next homework assignment, let's return.
No. I only require that the homework gets in on time, right? That first time. Because you can continue to update it as frequently as you want. Our grader, Lucia, is quite good. She turns it around. Basically, we turn it in on Thursday and they're done. So the quickest that you can get them in, anything that she doesn't grade, I'll grade. So if you give me something today that's updated, I can either grade it in front of you if you come to office hours, or I'll grade it when you're not there, right? Is Mia Guzman here? Okay, never mind. Why is this doing this? Well, there was a really cool picture here. Go back. No, this thing hates me. I was going to start with this really beautiful picture of an underwater explosion, but we'll just watch a video. So we love videos, right? Okay. So this is in Tonga, or off the coast of Tonga. That's big. That's real. These are lightning strikes. This is an underwater volcano. That's 100% real. Like a iPhone video. Pretty rad. This was so large that it messed up weather models for like years ago. So it injected an underground explosion, happened underneath the water, and then blew water up into the air. And so you can see the size here. It's enormous. That's the Pluto forest, and then it launched the tsunami, which is pretty remarkable. One of the things that always happens when I teach this class is always like something about climate happen during the course of the semester. Fingers crossed if it's not like a volcano like this or earthquake. We don't want those. We want like cool meteor showers. That would be great. Okay. And then it just like obliterated this island. It was nearby. Thankfully, no one on. But so this is sort of the power of. We'll talk about a little bit today. Processes like erosion and volcanism in reshaping the planet's surface. Okay, we're gonna have a lot of fun videos at the beginning, and then not so fun stuff later. Okay. All right. Come on. Okay, we also talked about runny versus goopy lava. And for folks who have not had a recent trip to Hawaii, I thought that I would show you what runny versus goopy lava looks like. Remember which one creates shield volcanoes? Runny creates shield volcanoes. Hawaii is a shield volcano. So let's have a look at what that looks like. Oh, this is a 6-minute video. We're not going to go 6 minutes here. Okay. This is very runny. So this is at night. Okay. So these are Hawaiian lava flows. There is some outgassing. This is where material comes from the interior of the planet, moves out both in gas and salt liquid form, in the form of magma or lava when it hits the surface. And here are some videos of it running, right? This is like a stream of magma catching stuff. This is in real time. Right? This is not sped up. It is burning up some force. This one I think is a time lapse, which is moving around a little bit. Really cool. You can see it seeping like a liquid. You've never seen lava before. This one's not as cool as the next one. The next one just blows me away. There are folks, these are people. That's a truck. This is the lava. Okay. This one's stupid. Oh, no, hold on. This one's crazy. Hold on. Why not work? Oh, God. Classic. No, this is all lava. This region here, that's all lava. It's all rock, basaltic. Let's see if this will work on this. Where it's red. Okay, so sorry this isn't working in the full screen mode, but hopefully you can see it okay here. So that's like a stream. That's all lava. So you stand there, you die. That is many thousands of people. Your phone there. And look, it's running like water. I told you that this is very runny stuff. So it comes out of the volcano and it moves down like a stream, right? And that's why you make the volcanoes in Hawaii, they're very wide as opposed to tall. So these streams, these guys are just chilling. I don't know what they're doing. I don't know that they're guys. But these folks are chilling, right? I assume that they work in some sort of volcanology. That I would never, you couldn't pay me to do that. Okay. This is running. This is running like water. Right? Don't autoplay. What are you doing? Outrageous. Okay, let's go to the next one. One more video, and then I'll show you some examples of explosive. And of course, everyone has this. Anyone not have TikTok? There we go. All right. Reasonable. Oh, okay. Let's do this video. They sacrificed their drone. Pretty sick. So it's pretty cool. I mean, volcanoes itself are the subject. It's also very powerful, as we just saw from the beginning, right? If we just look at it being the impacts that we see for sort of videos, it's very cool. But of course, they have very lasting impacts for the entire planet. This is anyone know what this mountain is? Mount St. Helens, very good. So on the left is before, and on the left is after. Sorry, on the right is after. So Mount St. Helens is a very explosive or volcano, right? At this time it's just mountain, and then not. And this is the same image taken, right? This is that same hill. You notice on the left, there are trees. On the right, there are not. Okay. So this was an example of goopy lava. And this goopy lava had a lot of gases inside of it. So when it finally erupted and came to the surface, it absolutely ruined the mountain, just exploded everywhere. There are some incredible images that I'm about to show you that are from someone who put their life on the line. They were not able to get away. They knew this thing was exploding. And their last act was to cover their camera so that they could preserve these images and they would then be obliterated. All of these trees were all destroyed, not by volcanic lava, but just from the air knocking them over, being so hot and pressing the trees down and catching them on fire. So this is the after, and this is the during. 10 seconds, 42 seconds, and of course we don't have videos, but people have used AI to interpolate between them. They're pretty cool, but that's not really scientific, right? That's like a version of science and art. And you can just watch, this is what the volcano looked like, and it was so massive that it destroyed the entire mountain in single seconds. Cool, right? Okay. Awe-inspiring? Okay. Let's look at the next one really quickly. So we have clickers theoretically. Everyone has them? All right, let's see if we can do this, Dr. Krismani. Let's see if I did it right. Yes. First try, yeah. Yes, I'll need you to find your limit sign. Is it too dark in there? Have like people sleep in the back. Okay, so this one is asking you to find out which planet is which. And there are, what did I do here? Okay, all right. There are 5 questions, right? So is it A, Mercury, Venus, Earth, Moon, Mars for this one? And then we'll do this one, and then we'll do this one, and then we'll do this one. Okay, so we're just gonna do the first one up here first. Okay. All right, all right. Lots of folks like the moon. What's that? Okay. All right, now let's try this one. What's this one? Yeah. Click in when you're ready. Top right, top right. What's this? Oh, this one's very confusing for folks. All right. Everyone voted who wants to vote? Okay, this one has it's interesting. A lot of people like the Earth, some people like Mercury, some people like Venus. Almost no one likes the moon and no one likes Mars. So turn to a friend, ask them what they got. If they got something different, ask them why. Just for like a minute. Okay, we got it. Everyone click in if you're confident. Now that you've had convinced your friend or they've convinced you, ready to get a hundo? Everyone click in? Okay, all right. Few people changed their mind, most people didn't. Or at least you convinced everyone like this. All right, that's interesting. All right, next one, let's do this one here. Bottom left, what's that? Click in. Of course, these are black and white. Hope that's clear. Yeah, I removed the color. I did some things.
So it's like normal colors, black and white, not infrared, right?
Yeah, these are all something has happened to some of these. Something has happened to one of these that you're going to be very upset about. All right, everyone's clicked in. Who wants to click in here? Okay, so lots of people like Mars, Venus, and Mercury. No one likes this for the moon or Earth. That's fair. That doesn't look a lot like Earth does. I don't know what these are. They're weird, right? Okay. Last one. This one down here. Bottom right hand side. Okay. No one likes this one for Earth. Okay. This one's kind of split. People like Mercury here and Mars. That's fine. Okay. So anyone want to argue for this one? Yeah, that's Mercury. That's Mercury. Yeah. 100% sure. 100%. Okay, good. All right, someone else? What's this one? Oh, come on, you gotta raise your hand. Just shout it out. That's Earth. Okay, what I do? What I do to this one? Yeah. No, it's not zoomed in. I did a different trick. I removed the oceans. This is the altimetry data. This is how tall stuff is. So that's Florida. Yeah. So that's Florida. This is what it looks like with no ocean. Okay, what's this one? Nice. What?
Yeah.
Venus. Okay. All right. Yeah. Good. What's that one? All right. Canceled. All right. Class is over. All right. Just kidding. No, that's too much to show. All right. So come on now. And we did this, right? I'm gonna kill this computer. All right. So we showed this at the end of last class. This was Mars. You guys can sit if you want. So this is Mars, and we showed all of the craters. So a grad student at CU Boulder went through and counted them all for his PhD. That was his whole PhD, just like doing that. Pretty impressive. And this is all of them. All right. That's all of them. This is also showing you the same type of altimetry, the altitudes. So this is closer to space, and this is deeper. And you can see there are a lot of them. And then I asked you to compare them to Venus. And I asked which one of these two bodies is older. This one or the last one? Mars is older? Yeah. So we were talking about the relationship between how many craters are visible and how young the surface is. I'm not talking about the planet as a whole. I'm just talking about how old the surface is. At the very beginning of class, we saw that a tsunami can wash away people's homes. It can wash away even islands, totally get rid of them. So there are processes that shape the surface and change it from its original state. This is very old surface that has not changed in billions of years. This surface, why is this not working? I'm upset today. Okay. This is very young surface. This is surprisingly young surface. I told you that this was about 600 million years old. I lied. I'm sorry. I didn't mean to. It's somewhere between 600 and 700 million years old. That's surprising because that means every part of Venus is about the same age as sharks. Okay. That's also very surprising. Why would the whole planet be the same, the surface at least, be almost the same exact age? Okay, we're going to get to this when we talk about tectonics in about 20 minutes. Okay? This should sit in the back of your mind. Hopefully you're confused. Maybe you're not. Depends. Okay. This is one of our favorites. This is Hawaii. Right? I promised to talk a little bit about Hawaii. So there's the Hawaiian Islands here. You go to the big one, Hawaii. There's Maui, there's Oahu. That's the only one I've been to. I hurt my toe on a rock there. I know that that's really important to you. And I swam with turtles, same trip. Not the turtle, the rock. Okay. Went to a first aid station there. Okay. This is a really cool, you'll notice just right away, this is the tallest one and it's the biggest one, and they get smaller going backwards. But there's multiple volcanoes on each one. They're shield volcanoes. They're creating these islands. And if you can look under the surface like we did in that clicker question, you would see the following. You would see all of these. They're called sea mountains or sea mounts. And they get smaller as they go backwards. So they're basically in a straight line, and then the straight line changes. And what's happening here is that there is a hot spot. There's a place in the crust where magma is coming straight up. Okay, so you can imagine that it's coming up like this. And the plate that we all sit on is moving like that. So it's moving like that. And as it goes across, you get new islands, whatever is directly above it. So what happened here?
Kind of shifted, huh?
Yeah. The plate changed directions. So this was the original direction, and now it's going this way. Okay, so that's sort of our more famous example, but we have a very local one, a very dangerous one. Does anyone know what the hotspot in the continental US is? What? That's a fault line, so that's like a slip like this. Talking about a place where magma is coming right up to the surface. Yeah. It is Yellowstone. Very good. This is Yellowstone. If you've ever been to Yellowstone, really beautiful prismatic lakes, places where you have geysers like Old Faithful. The reason for this, very scary if you think too much about it, is because you're standing basically on top of a lot of lava. Lava's just below you and it's heating the water, right? Boiling hot water. And the reason for that is this, basically, it's not a volcano in the same way that we think of volcanoes, because right there, the crust just has pockets of magma. So it's just very warm. And it's so warm that it melts rock. So what you see here, these are the Rocky Mountains, up and down, right? And there's just a giant carved out section. Looks like someone took an eraser and just erased the Rocky Mountains. Well, that's exactly what happened. Rocky Mountains were there, they're having a great time, and then they moved across this hot spot, and the hot spot just reduced them to flatness. And this is now very fertile farming ground. There's no volcanic worries in this region, but right here, big worry. If that explodes, everyone in North America is not having a good time. Okay? Questions about this? We'll talk more about tectonics in a little bit. Yeah.
So it is true that Yellowstone explodes, we all die.
I didn't say that. I said we have a bad time. Yeah. Yeah. We talked a little bit about how the dinosaurs died, right? So one of the ways is like that initial impact, and if you're close enough, yeah, you're having a really bad day. But one of the really horrifying ways to go is just like the idea of what is essentially a long winter. And I'm not talking like Game of Thrones, I'm talking about like you put enough dust in the air that the whole area gets cold. And you saw that with the smoke, right? But imagine that's the whole earth and all the plants die. Yeah. Okay, depends on wind. Right? So it's going to create a massive plume of dust. Right away, everyone in this region dead, right? Immediately. So like don't have any friends in Montana or Wyoming, they're gone. But like there's not a lot of people there, so it's okay. And then for the rest of it, you know, in the United States, you have the largest area of arable farmland. So that's like where you can farm. And just like now drop like tons and tons of ash on that. So now everyone's gonna die just because there's nothing to eat. So not good. Really not good. Okay. Yeah.
So millions and millions of years from now, basically Hawaii will slowly walk its way to another continent's location.
Yeah, in fact, if you go back to, I didn't show the scale here, but you know, when you're a dork and you don't have the internet, like let's say 90s kids, no one here maybe, sometimes you just open up an atlas and stare at it because you don't have anything else to do. And so you'll start to do that and you'll look at like geologic maps because they're available and free. And you'll see that this is Hawaii down here, and this is called the Aleutian Trench. Alaska is right here. This thing's big, big. Okay, I'll show another zoomed out version of that later. Cool? Oh, by the way, if you wait long enough, we become an island. Southern California is poised to become a beautiful island in the next like 10 million years. You just gotta freeze yourself. It's okay. Okay. All right. So Mercury and the Moon, boring. Ooh, they're dead. Geologic. Okay, nothing happened to them. They're just like nothing's happening inside of them. They don't have volcanism. They don't have any form of internal geologic processing. Yeah.
Does that mean their core is like cold or?
Yeah, we think so, probably. I mean, Mercury probably has a little bit of heat. It's debatable depending on which scientist you talk to. They're comparable sized. We'll talk about the difference in densities when we talk about the planets as a whole and what is making them warm versus cold. But for the purposes of this class, just consider there's no tectonics in a meaningful way on Mercury. There's no volcanism current on either, right? Like ongoing. And so if there's no processes to reform the surface, the only thing that happens is you continually hit it with stuff, impact crater.
Is that why Mercury rotates so slow?
Not quite. We'll talk about Mercury is a weird one. Will we talk about that? Maybe we'll talk about it when we talk about the Galilean planets. It's kind of a tricky question about like what are tides? Why does the moon show us the same face? And that's all sort of the same discussion. Why does Mercury have such a weird orbit? Okay. So we talked about impact craters and how that tells us about the surface. Here's some other examples. Here's our standard crater. But based on what you smash into, it can tell you a lot about what's underneath the surface. So let's say you smash into a region that has a lot of water under the surface, then the rocks become hydrated and they move. So just like you can imagine, you have some deterioration here of the edges of the wall. And you see this ejecta, remember we said you smash into it, we take all that stuff and we throw it around. On the moon, it looked like giant streaks, very long, bright white streaks. Here it looks goopy, like you smashed into mud. You threw the mud out, right? And this one, it's a big one, it's completely eroded. So you have something that's like nice and small and perfect, and look at those crater walls, look really like strong and stiff. And then here it looks more goopy, and this one's completely, right? So we have all these processes here that are telling us, oh wait, hold on, there you go. You have all these processes here that are telling us about how the surface can be impacted and then changed. On something like Mars, this can happen through something called erosion, which we'll talk about today. But on Mercury and the Moon, we think there's no reason for erosion, which you'll see. There's no volcanism currently, and there's no tectonics, which are going to change the surface. Okay? Okay, everyone's awake. What is that? Hands, not shut. Yeah,
Probably greater.
it looks craterish, right? But it doesn't go down. Yeah.
Like, called like the devil or something. Like that. Yeah.
Devil's in this class. No.
I think it's something like.
This is not in the US. Yeah,
It's like the site of the impact.
it kind of looks, yeah, it looks like it could be a crater, but it doesn't go down. Hands, yep, yep. Sorry, go ahead. Okay, I like that. So maybe it was an impact crater, but it, got filled in. Yeah, in the back.
Point out what you said one of the last classes. It's on the opposite side of the crater or down.
Damn. Okay, I did owe you that. I was supposed to show you Mercury. It's just not really that cool looking from the backside. I'll definitely show you this Thursday, but it's not as cool as volcanoes. Like, don't get your hopes up. It doesn't look like this. This is something different. Yeah. Ooh, I like that. I like that. So like melting from below, right? Kind of like we just saw with Yellowstone. Okay. No one, I was really hoping someone would say crop circle. No one said it. No one said aliens. I was okay. It's fun sometimes, to say no. I know, but it's fun to say no. Okay. So let me zoom in and I'm going to show you what this picture was when this first happened. God damn it. Okay. Oh, that's funny. Why are the trees all lying down? This is a place called Tunguska. This is, I believe, in Siberia. And basically what happened, something from outer space comes in, on its way in, catches fire. Sometimes that lights up the material inside. Remember, we talked about how you can trap gases inside the earth and make explosive volcanism. Well, what happens when there's gases trapped in the object that's coming in? It can also break up and explode. So this is called the Tunguska airburst. And that is almost a crater, but it's really a pressure wave. So this thing exploded above hand and it shocked, blew down all the trees, caught them all on fire. And there's this beautiful little scar. And the grass is like, chillin', do it. Because they got internal root system. Right? What? It's a bald spot. Yeah, exactly. Know nothing about that. Okay. Here's another example. Yeah, so you may be, hopefully everyone's alive for this one. 2012. No 12-year-olds in class. Okay, so this was the Chelyabinsk airburst. This is another example. One thing that's great about Russia is they all have these driving cams, these dash cams for insurance purposes. And so we have hundreds of these videos that we can actually triangulate which direction this material came from. It's really great for meteor science. Just because. Okay, all right, cool. So let's watch this one. So he's just going along his day, having a great time going to work. I don't know what you're saying in Russian. Nothing's happening yet. Nothing's happening yet. Oh, here we go. This thing is coming in from space. It's burning up. And it's real bright. It lights up the city. He just keeps driving. I'm so shocked. Nothing to go. All right, let's go. What? It's an average day in Russia, I guess. Okay. So okay, so what do you not do when you see this happen? What is your protocol? I mean, we all have the stop, drop, and roll when you're on fire. Everyone knows that? Yeah. Okay. And then when you feel an earthquake, you know to get under your table, right? Okay. Don't stand in the doorway. That's not necessary. Just hide under something. There's modern buildings for a reason. So what do you do when you start to see something like that? Right. Nothing. Just keep driving. Yeah, he's fine. Here's what you don't do. Yeah, don't run towards a window to look at it. Because, exactly, we just talked about the fact that these things blow trees down. Glass didn't stand a chance. So Russians who didn't know anything about this ran to the window. They're like, "Oh, pretty," and then got a face full of glass and had to go to the hospital. I mean, it's not funny, but it, it is. There is some. Anyway. So don't do that. Learning lesson. Okay. Questions?
Was it like you said, the scientists were near the window? Would it be those near the impact, or like say they just?
I mean, you don't know how far away that is, right? So we have it just to safer than sorry. When you see it, be like, "Oh, cool," and then run. Right? Because the light gets to you long before the sound. Think of it like lightning. If it's close to you, the lightning and the thunder happen right after each other. If it's far away, you see the lightning, and then a few seconds later, you hear the sound. The sound is what breaks the window. Okay? So it's like a big boom, and that's going to shatter glass. Okay? You want to watch it again? What? He just keeps driving. Yeah, he just literally doesn't respond, doesn't say anything. I don't understand it. I don't get Russian culture, but that's okay. All right. Okay. Yeah, no one put the brakes on. Not a single person was like, "Oh, that's wild." Okay. So here's what we're looking at. This is the different sizes of objects. Remember we talked a little bit about how these different sizes occur more or less frequently. And of course, the most common stuff to hit the top of our atmosphere is very, very small. These types of events are rare. So in fact, I can say, "Oh, the Chelyabinsk incident," and you know potentially exactly when that was. That's this one. 17, well, I should say 56 freedom units in diameter. So 56 feet in diameter. I don't know, that's like from there to there, right? Is that about right? Everything? No. 10 of us if we lay down. Yeah, 5'6". Okay. So that's Chelyabinsk. I made that nice air burst. This is the Tunguska one. And that was the one that blew down all the trees, bigger, right? This one didn't blow any buildings down or anything like that. It's windows. That's what actually made it. Yeah, so for example, you compare these two. This is the Barringer Crater one. That's the one in Arizona. Remember, he was going to go look for this one. This one was made of iron and nickel. So this one was very dense. And so it had a lot of explosive power when it hit. This one is basically made of like snowball material, very loosely packed. So would you rather be hit by a snowball or by a piece of iron? Right? You'd rather be hit by a snowball. And in fact, as it comes in, it starts to break up and explode. And so this thing, big, much bigger than the Barringer one, but never made it to the surface. So in fact, our atmosphere does protect us in some ways because it stops little things, right? By them burning up at the top of the atmosphere. Big things, okay. F word, okay? Cool. So this is a common example. Hopefully some of you have seen this. Have you seen this before? You don't know what it is yet. All right. That's beautiful, right? Some little pieces coming off. How big do you think that is? Oh, the size of a car. Size of a car? All right here. Anything else? Other sizes?
I want to say.
Maybe like a bus. A bus? Okay, let's go back for a second here. Let's use the example. This is a cruise ship. Okay, hold on. These are to scale. You guys are going a little too big here, okay? This Chelyabinsk here, right? The one that was bright enough to like light up the day during the day was not bigger than the room. Right? Let's put this into context. The first video I showed you was not bigger than the room.
So if that was in the room right now, how much the percentage of the room would pick up?
Excuse me?
So if that one, right?
This here, this is about the size of the room, right? From there to there. Okay? And that is big, right? Don't get me wrong. But, you know, we stop, the atmosphere stops, it breaks it up, creates this beautiful light show. Okay? So this one that just casually goes through the atmosphere can't be that size, right? Because we don't have that frequently. You know, a bus probably goes to about here. Right, from there to here. It's like a standard bus size, 28 feet or something. Yeah.
Does depending on the size, you know, matter like the light that we saw, you know, we saw the one from Russia, it's a little bit more, you know, different colors in the hole, it's still light, just
Yeah. So the one that you just saw was a little greener.
Yeah.
Right? Yeah, so that is telling you a little bit about what's inside of it. But that's something that we're not going to get into in detail. So, okay, so now that we've had that sort of like brain check, how big do we think this is? Size of a person, okay, much more reasonable, right? So now we're shrinking it down, right? So maybe a person made of rock coming in and burning up. Okay, would you be surprised if I told you this is probably no bigger than a baseball? More likely the size of a grape. Yes. Most times when you see a shooting star, it is the size of a grain of sand. The only thing is that grain of sand is catching on fire. It's burning up. It's catching on fire to something like 5,000 degrees. And it's moving quickly. And so it leaves every single atom that was inside of it is left on the sky. Okay? This is just like yesterday or so. I don't know. I just took a. Yeah, these happen all the time. This is not a big one. If you, yeah, I went on Wednesday.
That's what I saw last night.
What?
Then I saw this right. I think I saw.
No, this is an older video, but these happen all the time.
I was saying I probably saw one.
No, yeah. So there is a meteor shower, right? So I was last Wednesday. I went camping. And I just looked up and there's just shooting stars this big, this bright all the time. The problem is, right, everyone wants to get home safe, so they put lights out at night, and that's really bad for looking at the stars, right? So you want to drive safely on the roads. Okay. Does that make sense? So if you want to see something like this, you go to like the high desert or you go up into the mountains and just look up. And you'll see shooting stars like this all the time. Now, ideally, you want to go during a meteor shower, and we can talk about what that means. But that's just debris. And you can sometimes, one time I went to go see a meteor shower, and you know, one of these is called a shooting star or a meteor, and so they have rates. And the one that I went to was 120 per hour. And I was like, that's no way. That seems like bullshit. So I went and I sat there in my lawn chair on the top of the RV, and I started counting. 1, 2. We got up to 100 in less than an hour. And I was like, this is boring. You can literally get like so many just by being away from city lights. Yeah.
I would just say like they were once in a day because I did go to some high desert books. I'm literally not even. I think my last week.
Yeah.
I didn't see any.
Oh.
That's what I'm saying. Like, how frequently are you?
It depends on it depends on what time of the year, right? If you're looking for a meteor shower versus a random one. I would say that when we have observatory open houses, like the, you know, observatory open house nights, you can see one every couple days. Like, let's say you have 3 events per month, you get maybe 1 in those 3 events. Now, if you go during a meteor shower, depending on where you are and how illuminated it is, you can see them as many as 1 per second. It's a big sky though, right? Your field of vision is like this. So some of them are happening over there, you're gonna miss them. Okay. Okay, that was impact cratering. You guys have fun? These are all the versions of impact cratering. So you have the big ones, you have the small ones that burn up in the top of our atmosphere, and they're shooting stars. Let's talk about tectonics. Tectonics is disruption of the surface by the fact that it's moving, deforming. So this example here is of anyone who's ever been to Colorado. There's this place called Boulder, where you start with sandstone. That's the result of years and years of sedimentation at the bottom of the ocean, creating a rock. And then you take granite, which likes to live underground, and just like an ice cube that got trapped at the bottom of your drink, makes its way to the surface, it pushes up the sandstone and punches out these really beautiful layered sandstone deposits. So you can look at them and you can walk through them, and you would walk through time. The dinosaurs of one type would live here, and dinosaurs of another type, much older, would live below it. Not currently, they're all dead. Okay. Okay, so let's talk about tectonics. You know tectonics from San Andreas Fault, but these are some other ways of doing it. So we talked about the only thing you'll need to know for this class: hot goes up, cold goes down, right? And similarly, when you think about boiling water, hot goes up, cold goes down. So what this does is sometimes it brings bubbles in the case of your boiling. Sometimes it drags the crust in the case of the earth. So here you have an example. Heat from the interior is trying to escape and is moving up and stretching the planet. And sometimes you get little cracks in here. These are on Earth. This would be like a place, the Mid-Atlantic Ridge, where new seafloor is being created and magma gets to the surface and creates new crust. But then you don't just magically get to delete it. You know, the stuff is now moving and it runs into other stuff. And so you get compression. So here you have two pieces that are hitting each other and someone has to give way. So sometimes one goes above the other. That would be like the coast of Chile, where you have the Andes Mountains on one side and a giant chasm on the other underwater. Or you have them both smashing, like Mount Everest. It's mountains that go real tall up. So these are all examples of tectonics. This is the Appalachians. So this is compressional here in the US. And then this is on Mars. That's extension. So that's the process of spreading apart the crust, and then it cracks in ridges. Okay. You have to have a warm interior. So Mercury and the moon don't do this because it no longer is warm in the interior. We, on Earth, continue to have this. And when I say tectonics, it can be global or local. It can be plate or non-plate. We are most familiar with the fact that we live on plates, and I'll show you a cool picture of that, right? We think there's good evidence to suggest we are the only planet with plates. Okay, not just dishware. Okay. So how can solid rock be bent, squished, stretched, and cracked? Yeah.
It's hot.
It's hot, good, yeah. Yeah, anything else?
Amount of force, like impact.
Okay, yeah, so like if you smash into it, you can deform it very quickly, good. Any other ways?
Sheer time and repetition.
Very good. Okay, so over really long time scales, we might not think of how hard things are. Okay, so rock acts like silly putty if you wait long. And the way that you could think about this, right, is like however I'm stressing the material is going to depend on what the result is. So if I do something on a very short time scale, I might crack it. Right? So for example, I smash into the surface with an asteroid, I could deform it very rapidly, and I'm going to break it all up. Right? Maybe I melt it really quickly. Whereas if I do it very slowly, I might think of it as like bending. Maybe I should buy some silly putty for class, and then we can show how that works, right? So you have this material that can stretch and flow, but then appears hard. in some circumstances, right? And of course, it depends on the temperature. So we saw this example at the very beginning. If it's warm, then it flows more readily, right? What would an example of that be that I showed? Yeah, running lava, right? We saw that at the very beginning. When it's hot and it's molten, it's like ready to go. Whereas like you go and you look at rocks and unless you kick them, they're not going anywhere, right? They're not slowing down the hill. Okay. So when rocks are low temperature, they tend to be more brittle. All right. The crust where we stand, pretty low temperature, right? Fairly comfortable. You can lay down on the ground quite often. I would not recommend laying under the ground, right? That would be higher temperature. That material flows, right? Okay. And here's the example I wanted to show you. Really cool art, right? Okay. So here on the top, you have Earth. So you have places where it's melting, like the hot spots of oh my God, Hawaii and Yellowstone right here. Good. And then this example here would be like the Andes. We have a plate that's going under, and then it's causing some wonderful mountains, some really, really tall places. And then you have some continental crust, which is a different kind of crust. I'll show you that example later. Whereas like Venus is kind of weird. We don't think that there are individual plates that are broken, so they can't go under one another. It's just one giant lid. And you just get squishing. So if I get melting over here, it has to go somewhere, and it causes squishing in other places. So it kind of looks like this. So in the center, I have a volcano that's producing material, and this has to get out of the way so it cracks and it crushes, right? It's like if you took a can and you squished it. It would crumple up like an accordion. That make sense? And these are big, right? These are like 100 kilometers across. So these are giant cracks. Okay. I said Venus. I shouldn't have given that away. Okay. Here's the Earth. If you've never seen the plates before, these are the plates. You are here. You are on the Pacific plate. That is different from the North American plate. They are passing by one another, like ships in the night. The reason that there are earthquakes in California is because one is moving like that, and they're slipping past each other. There's a big slip. Everyone goes, ooh, you freak out. We're really hoping that we get a big one, and then all the people who came here from Ohio go home because they're scared, and property values go down, and I buy a house, right?
They've been saying that, oh, the big one's coming, the big one's coming. It's like,
Yeah.
how long have they been saying that?
Well, that's a good thing to say. The big one is coming. But the prediction game is hard, right? Don't invest because you think that the big one's coming. Don't invest or divest because you think Yellowstone's going to explode, right? That's not how we live our life. Hold on, let me show you a couple more examples here. So here's the edge. This is weird line. That's the Mid-Atlantic Ridge. This is a location on Earth where the plates are coming apart. This is a place where hot magma is going upwards and dragging the plates apart and creating new crust in here and pushing apart the crust, like parting the Red Sea, right? And you'll notice the evidence that this was happening at all comes from very careful looking at a map if you're a dork, right? So you look at the edge here and you look at the edge there and you go, huh, I could like put those together. And that's exactly what they were. At one point, those two pieces were connected. And we can find this in terms of the geologic record. This is the same type of rock. We find exactly the same fossils. We found the same footprint of the same animal on either side, which is pretty wild. So these were probably connected at one point, and this split them apart. That is Iceland. Iceland's having a volcanic time. because it's right on top of a place where the planet is moving apart. Similarly here, I told you that this is the edge of the Andes, and this is the Nazca plate. So this thing here is going under this one. So big rocky rock, tall rock, volcano. Okay, on this side, cutting through, right? Earthquake. Okay, on this side, this is the Ring of Fire. It's called that because there are hundreds of volcanoes all the way through here. All of Japan is volcanic, right? Cool. It's an island chain due to the fact that you have seafloor or some continental crust going under, or sorry, seafloor going under and pushing up magma underneath right here. So if you look at the plates, it explains a lot of the geology. And this one here, you'll notice here's India in a head-on collision with the Eurasian plate. And that is creating the largest mountains on Earth.
What is the purple spot on the side of the Arabian plate and the African plate? The only area on the right.
Here?
Yeah.
Just very old.
Very old.
Yeah, these are ages here. So this is young, brand new friends right here. So this is brand new. Right, all of this material is getting made today. You can't see it. This is not very good, right? This is kind of like smeared out. There's a brand new little dot, one little dot in there, right? But you'll notice here, this is 280 million years old, right? You see anything older than that? Very young surface, very new. Now, these are not colored. The continental crust is older. But we're going to get to that when we get to Earth as a whole. Okay. Wow, this is really not going as fast as I thought it would. Okay, we're going to pause here because I've been talking for a long time. And I need you to start thinking about one thing. This is from the surface of Mars. Okay. Oh, God damn it. What does that say? Set up professional? I don't know what that is. Okay, there you go. It's literally exactly over what I wanted to show. Okay, so what is that? Yeah, that's Phobos. Its moon right here is in a crescent form, like that. And then right next to us, or not. And it's right next to us. So everyone you've ever known and loved is right there. Yeah. Yeah. So it's very similar. I mean, this is right at sunset. And so this is the phase of Phobos. And you've all been reading the book, right? Good. And you know that tonight is a very unique night. Come on now. Tonight there will be a lunar eclipse. Oh, interesting. It's partial. Don't get your hopes up. We are here. So we will see it. Okay. And here's when we'll see it. You need to subtract 3. This is all Eastern time. So note that it starts over here at 5:45, 5:40, right? So that's like 45 minutes. Okay, go out. Look for the moon. You know where it'll be? What? Behind the sun. Not quite. This is a partial lunar eclipse. A solar eclipse, you'd be right. In the east. Look in the east. Right? If you don't know which way east is, just pull out your phone. There's a compass. You can do that. Okay? All right. So that's when it starts. And we'll watch it, throughout the night. And at 7:45, set an alarm and go outside. Okay? 7:45. Leave class. Who cares? Okay. Oh, for Astrolab? Yeah, definitely leave class. Tell them that I 100% allow that. Okay, so now we want to do what the fuck is the moon and why does it not show phase? Bad at reading. Oh, brutal. Okay. All right, so we are going to figure out, take a few and pass them down. two to a person. Two to a person, find a friend. And we're going to explain why the moon has stayed. No. Yeah, one piece, two people per. Okay, you and a friend share one. I'm back, my bad. There. Two people per paper. If you're three people, move over. Or turn around. You can also turn around. That's legal. Yeah. Let me know if we don't have it. There should be exactly. Anyone else have extra? Make sure you pair up. No one doing this individually. No one's hoarding them, right? Yeah.
Yeah. That's like.
And there is like just randomly on the last page, there's nothing on it. That's an accident.
When it's here, it's. Right here. Yeah.
Sorry, I didn't make it.
This side is dark. This side's dark.
I didn't see you stop that.
Saw them like.
When New York.
I saw some.
She was like,
I couldn't stand that.
Yeah, no worries.
Yeah. Yeah, yeah. Yeah, that's what you're saying, circle them, so
You got your.
Question, so on my, on Canvas and eventually, even though I think I printed it last Tuesday and I picked it back on Thursday.
Oh yeah, you weren't supposed to pick them up. I didn't tell people that. These don't come back to you. I keep
Oh,
these.
okay, okay, my bad.
Yeah, it's okay. No, perfect.
Thank you very much.
If, yeah. What? No. Keep it, you can turn around Thursday. We'll start at the beginning of class. Okay? So it's 5:15. We're not legally allowed to keep you any longer. You can all leave. But please pick up your homework. Homework 2 is alphabetical. See, I learned. Okay? This is between R and F. And this is between A and M. If you haven't gotten homework 1, please check that here. Okay? If you want to turn in the lecture tutorial, turn it in here. And check online to make sure that I have what you've turned in. 0 means I didn't get it. 1 means I did. Dash means it's excused. I guess I should have started with that. Yeah. Yeah. Thank you. Well, lecture tutorial is here. Sorry. Didn't finish, feel free to turn it in on Thursday. Yeah.
Yesterday,
Uh-huh.
in regards to the homework.
Yeah.
I done today, but for whatever reason, I